Welcome back to Differential Equations. This is the second part of our lecture on finding a second solution and reduction of order. In this part, we'll be getting to all of our actual examples. All right, so let's think back to part one. We were talking about a differential equation having two solutions, y1 and y2, and trying to determine if those two solutions were linearly independent. We left off with a theorem using a quantity called the Wronskian, which answers that question of when two functions are linearly independent. So let's start this part by summarizing an important result. A second order linear ODE always has two linearly independent solutions. And again, linearly independent means at a basic level, different. So a second order linear ODE always has two different solutions. Those two solutions, we'll be using them to build up all other solutions. Well, this lecture, we're going to focus on how to find a second solution. Now, let's start with this example here. And I'll point out one of my favorite problem-solving techniques from physics, guessing. So pause and see if you can guess a solution to this differential equation. All right, now if you've guessed a solution perhaps as e to the x, you're right, that is a solution. Plug it in, and it satisfies the ODE, it works. So y1, we can say is e to the x, and it is a solution. Well, the important remark right above tells us that we should expect there being a second linearly independent solution. Now, sometimes in a differential equation, it's easy, perhaps like this example, to guess one solution. But how do we get all solutions? Because again, we're expecting there to be two linearly independent solutions. All right, how do we find this second solution? Well, as it turns out, there is a way to do this with a similar substitution or kind of a algebraic kind of equation from what we did with a homogeneous ODE. All right, and if you scan to the bottom of that statement there on the bottom, y2 equals u of x times y1, well, that looks very similar to our substitution for a homogeneous first order ODE, y equals u times x. All right, now it's not quite the same, but it's very similar. So again, as you progress through higher level mathematics, sometimes you try to reuse results that already worked, and we generalize it a little bit. So we kind of change y equals u times x, we transition it to this, y2 equals u times y1. All right, and in this, we're assuming that y1 is a known solution to a second order linear ODE. And what this substitution or equation tells us is there is always a way, given one solution, y1, to find a second solution. y2 equals a function, u of x, times y1. And this is actually kind of remarkable if you think about it. It basically says that for a second order linear ODE, that somehow a second solution is encoded like DNA within a first solution. And that's kind of interesting if you think about it. All right, what we're going to be getting to, all the work, all the fun algebra, is implementing this result. Now, it's actually really simple if you conceptually understand what y2 being a solution means. It means if you take y2 and plug it into your ODE, it would have to satisfy it. Now for us, with a second order linear ODE, in order to plug y2 in, we're going to need y2, y2 prime, and y2 double prime. So there's a few simple steps here to go from having one solution to getting a second solution. All right, we're going to start with the second solution, y2, as a function u of x times y1. Keep in mind, we are kind of supposing we know what y1 is. In the examples, you'd be given y1 already. All right, there's some work here, typically using chain rule and product rules to calculate y2 and its derivatives in terms of u and its derivatives. All right, we're going to plug all those expressions into the ODE and kind of work backwards to solve from that equation for what u is, or u of x, with that technique we briefly introduced called reduction of order. All right, when you're ready, let's take a look at a first example, which is kind of what we have highlighted here in the upper part of our screen. We're going to use y1 as e to the x as a solution to that differential equation to find a second solution. All right, now if you feel that you understand what's involved for this, by all means, give yourself an attempt, pause, and I would say maybe anywhere from 5 to 10 minutes, getting used to the algebra and the different calculations involved here. If you don't feel comfortable attempting this, we'll wait a few seconds and just go through this together. All right, now this is a good one to show you how all the different steps fit together. You might be able to guess a second exponential function as a solution, but I don't want to give it away. Let's see how the procedure works. All right, so we're given y1 as e to the x, and we assume a second solution, y2, as a function u times e to the x. All right, to avoid any confusion with x being a variable that we're multiplying by, let's get rid of the function of x notation and just keep in mind that u is a function of x. All right, a little bit of work here to calculate y2 prime and y2 double prime using the product rule, but pretty straightforward. All right, and we're going to want to simplify that by factoring e to the x out from each of those terms. All right, now with that simplified factored version, we're going to calculate the second derivative. If you use the unsimplified version, you'd have to use the product rule twice. So let's be lazy. Let's use the product rule once. Let's use the factored version for y2 prime to calculate y2 double prime. All right, go through the product rule yet again and factor out e to the x. And you should, for minimal effort, get these expressions for y2 prime, and y2 double prime. All right, a little bit of work there, but hopefully not too bad. We're going to plug all those in to the ODE. Now the differential equation is y double prime minus y equals 0. Now if y2 is a solution, and we want it to be, y2 double prime minus y2 has to equal 0. It has to satisfy the ODE when we plug in y with y2. All right, let's take all of our expressions and plug them in. Here, we only have y2 double prime and y2. We don't need to plug in y2 prime. All right, and if you're careful with your signs, you should get to here. And this is a good place for me to mention what must happen for reduction of order to work. The u terms must cancel out completely. And what I mean by that is the u term by itself, not u prime or u double prime. Only the terms involving the function u must completely cancel. And again, that's in order for reduction of order to properly work. All right, if you either kind of factor e to the x out from that, expand, and then refactor, you'll find that the u, e to the x terms do cancel. All right, so we get this slightly simplified version. Satisfies what we want. There is no u term. Certainly find that there's u prime and u double prime. And we can simplify this a little bit. We can divide e to the x off, since we're mainly just focused on solving the differential equation part for u. All right, so again, notice it satisfies our check. There is no function or u term here, only u prime and u double prime. We can use reduction of order, z equals u prime, and as a consequence, z prime equals u double prime. And if you plug that in, we get this first order ODE that is easily solved by separation or as a linear ODE. Now you should pause to attempt that. We'll check in about a minute. Welcome back. Hopefully that was pretty well. I think this one goes really quick if you solve it as a separable ODE. All right, and if you do that, and again, we already did that in part 1 of this lecture, just with different variables and symbols, you should find that z equals a constant times e to the negative 2x. All right, we can back substitute z as u prime. Remember, our goal is to solve for u, or u of x. And again, we have a very simple integration here. And if we integrate, since c is a constant, the negative 1/2 that we would get by integrating just gets absorbed into it. So we get u here as a constant times e to the negative 2x. Now, I want to briefly mention why we can get rid of the constant multiple c in this expression for u. To put it briefly, y1 and y2 will be part of a linear combination. So we will already be multiplying y1 and y2 by constants. We don't need to multiply by extra constants here. Again, a constant times a constant is, oh yeah, another constant. All right, so we can drop that constant multiple c and just say u of x is e to the negative 2x. Now, u itself is not a second solution, but u times y1 is. So if we go back to the beginning, we now know what u of x is, e to the negative 2x. And if you plug that in, and just be careful with manipulating your exponentials, e to the negative 2x times e to the x, add the exponents, you'll get y2 as e to the negative x. All right, this is a good first example. The calculations aren't too difficult, but it shows you everything involved. And we can even tie this back to our result on the Wronskian, just to verify that these actually are the two solutions that we want. Y1 and y2 here are linearly independent. So if you check, use as y1 e to the x, y2 as e to the negative x that we just found, you can show that the Wronskian comes out to be non-zero, which means those two functions are linearly independent. All right, when you're ready, we'll take a look at a second example, maybe a little more challenging work, only in maybe calculating the derivatives. That might get a little more tedious. But the algebra here is pretty representative. When you're ready, let's go to example 2. All right, so same exact type of question, just a different second order linear ODE, which means we have different solutions. So here, the solution that we're given, y1, it's e to the 2x, and we're going to use the same procedure, reduction of order, to find a second solution, y2. Now, maybe you feel a little more comfortable making an attempt. Give yourself maybe 5 to 10 minutes for example 2 if you want to attempt it. We'll check in after that. Welcome back. Hopefully you were successful with this. This only gets more tedious for calculating derivatives, which is Calc 1 material, and maybe a little more tedious with the factors of 5 and 6 there to keep track of terms, multiplying and adding, which always plagues us as we move in through higher level mathematics. All right, so let's go through this at this point. Just be careful for a common error. Make sure you realize you're going to use the chain rule here when you differentiate e to the 2x. Each time you differentiate that exponential function, the chain rule gives you an extra factor of 2. So if you couldn't get it to work out in your attempt, that might be why. All right, you still want to use the product rule here since u, a function of x, is multiplying e to the 2x. So to calculate y2 prime and y2 double prime, you would use the product rule and the chain rule. All right, since at this point you're probably comfortable seeing when you differentiate exponential functions, they keep coming back. So for all these derivatives, we're factoring out e to the 2x. All right, so that's one thing to check. Again, just Calc 1 level, product rule and chain rule. You should be very comfortable with that in our course, differential equations. All right, we're going to plug all those expressions into the ODE. Just be careful with parentheses for the factor of 5, or really -5 and 6. All right, and you can expand. And what you should expect, recall, for reduction of order to work, you want the u terms to cancel out completely, leaving you with perhaps u prime and perhaps u double prime. But you definitely want the u's to cancel out. All right, and if you're careful with your algebra, you should find that that happens. And we get what we want, a differential equation with no u term, so reduction of order will work. All right, so let's implement our reduction of order trick, or substitution, or change of variables. And this one should be very straightforward. Just take a look at an intuitive level, what that differential equation for z says. You're looking for a function, z, that equals its own derivative. That should be e to the x. You can easily solve this as a separable ODE to find that. And if you substitute back z as u prime, you can integrate, and the integral of e to the x is itself. All right, so we get our function u. We can multiply u back to y1 to get y2. So a second solution would come out to be e to the 3x. E to the x times e to the 2x. Add their exponents, giving you e to the 3x. All right, we can again check that these solutions, y1 and y2 that we just found, are linearly independent using the Wronskian. So just make sure you can verify that. Not needed for this problem, but good to tie it in. Just be careful with your exponential factors. e to the 2x multiplying e to the 3x would come out to give an e to the 5x. And there's some terms that cancel out, leaving you with that for the Wronskian e to the 5x. All right, that verifies that these two solutions are, in fact, linearly independent. All right, now at this point, hopefully you're getting more comfortable with how this works. I'll give you one last third example, but at this point, you've pretty much seen it all. So pause, give yourself, again, 5 to 10 minutes for this, and we'll check in at that point. All right, welcome back. So we're going to go through this one a little quicker, just so because it's the same work. Hopefully you're starting to get the sense for all that goes into one of these problems. All right, first thing, y1 is just x. And be careful with your notation here. We're going to drop u of x. We're going to drop the function of x notation and just write y2 as u times x. Again, realizing that u is itself a function of x. All right, this is just a straightforward product rule calculation to get y2 prime and y2 double prime. And we can just plug those in to the differential equation. Be careful with the factors in front of y double prime and y prime, x squared and negative x respectively. They're going to distribute across the parentheses or through the parentheses. All right, just be careful with your distributions and multiplications and signs. And you should find that, in fact, again, the u terms cancel out, leaving you only with terms with u prime and u double prime. Now this one, we can simplify it slightly by dividing by x squared to get this differential equation, u double prime times x plus u prime equals 0. At this point, we can now implement our reduction of order trick, and I'll leave the details for you. You should find, if you have done it correctly, that u works out to be natural log of x. And if you plug back in, that then means that y2 would be x times natural log of x. All right, that concludes everything I wanted to cover for our lecture here on finding a second solution. That's pretty much these last 3 examples, which involved a technique known as reduction of order.